This is 7.3 in Math 31, which is where we start to look at the derivatives of the other trigonometric functions. And really other, because we've only looked at sine and cos, means tan, secant, cosecant, and cotangent. And students typically don't like hearing that because they don't like reciprocal trig ratios for whatever reason that is. We have to get used to that. Reciprocal trig ratios are nice to use because if we can write it as a single trig ratio, it actually makes an application problem a lot easier. The way that we're going to do this is we're going to go back to some of our kind of classic techniques, being the quotient rule for the most part, and we're going to look at how do we take the derivative of tan x. Because instead of dealing with the derivative of tan x, what I can say is that if y is equal to tan x, I'm going to instead say that y is equal to sine x over cos x. Now, this does certainly have non-permissible values where you cannot take the derivative of it, but we're going to assume that they meant take the derivative over its existing domain. So we are just going to take the derivative, and I say just like it's easy. It's not easy, but we are going to take the derivative of sine x over cos x using our quotient rule. So dy over dx, immediately I'm going to write that original numerator squared. So cos x is squared on the bottom. The derivative of sine x, and this is where going back and making sure you know how to do these comfortably is important. Derivative of sine x is cos x times the original denominator, which is still just cos x, minus the numerator, which is sine x, times the derivative of cos x, which is negative sine x. Well, what that gives me, and I can clean this up, and we do want to clean it up, we're going to get dy over dx is equal to cos squared x plus, because it's a negative times a negative, sine squared x, all divided by cos squared x. Now, don't get too cancellation happy. Those cos squareds don't cancel. There's two terms in the numerator, so we can't do that. But on your formula sheet, you do have the identity that sine squared x plus cos squared x is equal to 1. That's our unit circle, right? So I'm going to make that substitution, and that means that dy over dx is equal to 1 over cos squared x. 1 over cos squared is secant squared x. And the kind of little summary there we're going to have on another page, we can say that d over dx of the tan of just x is equal to secant squared x. But I'm going to do it for this one and probably for the others as well, that if we wanted to look at this in a more complex form, so d over dx of the tan of a function would be equal to the secant squared of that function times its derivative. And that is just the chain rule. But I think it's always important to remind you that you need to consider the chain rule when the argument of whether it's sine, cos, or tan is more complex than just a variable. So I like writing that extra piece in, and you'll see me do that a fair amount throughout this lesson. All right, next up is use an identity to determine the derivative of cosecant. So to find the derivative of cosecant, instead of just trying to, and by the end of today, hopefully we'll be able to do this, the derivative of cosecant x is equal to the derivative of 1 over sine x, because cosecant x is 1 over sine x. So to take the derivative of 1 over sine x, again, it's a quotient rule. You do have an option here. There's two ways of doing this. I'm going to do it as a quotient rule, and I'm going to show you a chain rule to do it as well. If we did it as the quotient rule, we would immediately have sine squared x in my new denominator. The derivative of 1 is 0 times the denominator, which is sine x, minus the numerator times the derivative of the numerator. And what I get is negative cos x over sine squared x, which can be written a little bit differently. I can write that as negative cos x over sine x multiplied by 1 over sine x. And the reason why that's a benefit is because I can actually represent that as two different trig functions, or trig ratios, I should say. Negative cos over sine is cotangent, so this is negative cotangent x times cosecant x. So the derivative with respect to x of cosecant x is negative cotangent cosecant x. These are trickier derivatives. I believe that they're on your formula sheets. You don't have to memorize them. If you ever forget them, I would recommend that you go back to first principles and find their derivatives that way. All right, next up, oh, I went the wrong way, sorry about that, is secant. Secant is 1 over cos, and I'm just going to, not belabor it too much. We're going to take the derivative, and I want to show you that the derivative of 1 over cos x is the same thing as the derivative of cos x to the power of negative 1. And we could have done this in the previous example, as sine x to the power of negative 1, but I'd like to show you at least a couple different techniques as we go. And if I take the derivative of cos x to the power of negative 1, what I get is negative 1 times cos x now to the power of negative 2 multiplied by the derivative of the inner function, which is cos x, and the derivative of cos x is negative sine x. Well, if I clean that up, what I get is sine x, because the negative one and the negative cancel, divided by cos squared x, because that's in the denominator. It's a positive exponent now. And I can write this as sine x over cos x multiplied by 1 over cos x. And what that allows me to say, and I'm going to summarize this on the bottom, is that this is the derivative with respect to x of secant x, and that's equal to tan x times secant x. Now again, that is if the inner argument is just x, but that happens a lot, so it's something we have to get used to. If it was required, we may have to do the chain rule, and you will likely have to do the chain rule a lot of the time when you're dealing with trig functions. All right, one more, which is the cotangent. Cotangent is cos over sine. You can't really rewrite this. You could write this. I shouldn't say that. I just do want to write it. I'm not going to do it this way. I like the quotient rule. But you could write this as cos x times sine x to the power of negative 1. And then do that or take the derivative as a product rule with a chain rule piece within. But I am going to just use the quotient rule. So I'm going to apply the quotient rule to this quotient up here, cos theta over sine theta, and that's going to be equal to sine squared x on the bottom right away. Derivative of cos x is negative sine x. The sine x denominator is still there. Then I'm going to subtract cos x times the derivative of sine x, which is cos x. And what that gives me is that the derivative with respect to x of cotangent x is negative sine squared x minus cos squared x all over sine squared x. Now that gets tricky because there doesn't appear to be an identity that has negative sine squared minus cos squared, and there isn't. What we have to do is a little bit of factoring. So I'm going to say that the derivative with respect to x of cotangent x is a negative 1 times sine squared x plus cos squared x. So I factored a negative 1 out of the numerator. What that allows me to do is I can use the identity for that bracket, and this becomes negative 1 times positive 1, because sine squared plus cos squared is equal to 1 over sine squared x. That gives me negative 1 over sine squared x, which can be written as negative cosecant squared x. All right, a lot of work going on there in those questions. I know that you're not really going to have to prove this, but it's important to understand where they come from. This, if I can go the right way, is what you need to know. The derivatives of the 6 trigonometric functions. So there's sine on there, there's cos on there. If we want to talk about bare minimum, I would argue, would be the primary. You need to have these memorized. From there, you may be able to derive the other ones. Honestly, it's a good idea to know all 6, especially if you're planning on, some kind of a mathematical discipline, because these do come up more than you might expect. And then the rest of the notes are just going to be working through some examples. I think I'm going to do a couple on this page because the last few examples are a bit tricky. So we are going to differentiate a few functions along the way. A lot of these come from different applications, but one of the most useful things in a question like this is you could use the quotient rule, but I think I would rather see this equation as y equals the denominator, 1 plus tan x to the power of negative 1. And the reason why that's so useful is because then it is at least a relatively simple chain rule. So if y is equal to 1 plus tan x to the power of negative 1, y prime is equal to negative 1 times 1 plus tan x to the power of negative 2 now, multiplied by, okay, now we're going to take the derivative of the inner function. The inner function is 1 plus tan x. The derivative of 1 is 0 plus the derivative of tan x, which is secant squared x. And in this case, because the innermost function is just x, we don't have to write multiplied by 1 at the end. But what I do need to do is to kind of clean this up as much as possible. So I'm going to have negative 1 times, 0 plus secant squared is just secant squared x. And now in my denominator, I have 1 plus tan x to the power of 2. And that's certainly, a perfectly acceptable way of leaving that answer. The one thing that you may want to do to write this, perfectly is apply the negative on there. So I'm just going to put or negative secant squared x over 1 plus tan x to the power of 2. A bit of an ugly derivative for sure, but it is important that this is just an application of the rules that we've learned throughout. It does take practice, and it takes a lot of it, unfortunately. Well, fortunately, math is fun to do, right? All right, next example is again a little bit trickier. It's y equals 2 times the cosecant cubed of 3x squared. One thing I'm going to do is I'm going to write this a little bit what I think is friendlier. So this is going to be 2 times, and then what I'm going to put is in a square bracket, I have the cosecant of 3x squared, and then all of that is cubed. And if nothing else, I think that makes it a little bit easier to take the derivative. So y prime, I'm going to take that constant out, so it's going to be 2 times, and then the derivative of something cubed is 3 times that something, which, if I can write it correctly, is cosecant 3x squared, and now it's to the power of 2. But what I need to do next is I need to multiply by the derivative of that square bracket. The derivative of cosecant something, so cosecant x, is, and this is where it gets a little bit hairy, it's negative cosecant, the inner argument stays the same. So it's negative cosecant 3x squared times the cotangent of 3x squared. And as if that weren't enough, we have to consider the derivative of the innermost function. The innermost function is 3x squared. The derivative of 3x squared is 6x. Now, this is a great example of where the derivative of trig functions can get a little bit unwieldy. You know, like that is a pretty complex expression, but it's important that now all we're going to do is multiply what we can and simplify. So I have 2 times 3 times 6 times x. 2 times 3 is 6. 6 times 6x is 36x. What I have is the cosecant of 3x squared squared, and then the negative cosecant of 3x squared. So I'm going to put the negative in front of my 36, and then I'm going to have the cosecant cubed of 3x squared. And then finally, I'm going to have that cotangent of 3x squared included as well. And that is a very ugly looking derivative, but applying the chain rule basically twice in this situation yields that result. Okay, one more, and then I'm going to switch in, or I'm going to make a part 2 because the last 3 examples apply some actual, useful information. Oops. Okay, it says tan y is equal to x squared. Now, the one thing we're not going to do in this course is we're not going to manipulate for y and say that y is equal to the inverse tan of x squared. That is a valid way of doing this question, but we haven't learned those derivatives. The derivative of arc sine, arc cosine, arc tan are in AP math, but they're not in math 31, so we're not going to do them. So instead, what I'm going to do is right off the bat, if I want to know what dy over dx is, what I need to do is introduce the derivative on both sides. So I'm going to take d over dx of the tan of y, and that's going to be equal to d over dx of x squared. Now, the derivative with respect to x of the tangent of something is secant squared of that something. But then I have to multiply the derivative of the inside. The derivative of y with respect to x is that Leibniz piece, that dy over dx or y prime. And then on the right-hand side, this is pretty classic derivatives, it's just 2x. Now, we likely want to know what dy over dx is equal to, so I'm going to divide by secant squared. I get that dy over dx is equal to 2x divided by the secant of y squared. And then really importantly, secant x is equal to 1 over cos x. So logically, 1 over secant x is equal to cos x. They're reciprocals of each other. What that allows me to do in this final form is because we have 2x over secant squared x, I can write dy over dx as 2x times the cos squared of y. I would take either of those forms. They're both perfectly acceptable. In general, though, students would rather take the cos of something than the secant of something because it's a little bit easier with our unit circle.